Good afternoon, everybody. In this lecture, let us discuss on the characteristics of the laminar boundary layer, then the thickness of the laminar boundary layer, the shear stress at any point if the boundary layer formed is laminar, and what is the resistance, that is drag force on one side of the plate, and if the flow is there on the other side also, then on both sides of the plate. Then similarly, if the boundary layer is turbulent, all these things. Number one is thickness. Number two is shear stress at any point. Number three is the drag force on one side of the plate and drag force on both sides of the plate. Then last, if suppose the boundary layer is laminar up to certain extent and then remaining is turbulent, then naturally the thickness we can calculate depending upon whether the boundary layer is laminar or turbulent. Similarly, the shear stress is also at any point you are calculating it. That's also no problem. But the drag force when you are calculating on the entire plate, some portion is laminar, some portion is turbulent boundary layer. So there a little bit difference is there. That also we discuss. This topic helps us in solving many problems in the case of boundary layer theory, wherein how to calculate the boundary layer thickness and at the same time how to calculate the resistance force that the flat plate encounters when the flow takes place over it. So that's the basic thing, right? Let us start. So in today's class, what we are discussing topic by topic, I will explain to you. First one is explain the characteristics of laminar boundary layer, state the equations are laminar boundary layer thickness, shear stress at any point, and the drag force on the flat plate. So this is the problem. So now let us take one after the other. Laminar boundary layer exhibits all characteristics of laminar flow. That is first. Then second one, the velocity distribution is very, very important. It is parabolic. Thickness of the boundary layer is proportional to root x. That is, the thickness is delta is proportional to x to the power of half. That is third point. The fourth point is laminar boundary layer exists up to a Reynolds number of 5 into 10 to the power of 5. Up to that, that is Vx by nu is equal to 5 into 10 to the power of 5. Up to that, actually, strictly speaking, it must be less than or equal to. Kindly remember. So if you remember this, generally the Reynolds number actually for laminar boundary layer may vary from 3 to the power of 5 to 5 into 10 to the power of 5. This is the variation. Next, the most important point, the equation for laminar boundary layer thickness is equal to, because the derivations are not there in the curriculum. So only we need to note the equations and work out the problems. So it is delta by x is equal to 4.91 by root rex. Some textbooks write 5 by rex also, doesn't matter. Where delta is the thickness of boundary layer, then x is equal to distance, where where we find boundary layer thickness along the plate. Then Rex is equal to, it is Vx by nu, where V is the velocity, X is equal to the distance already I mentioned above, then nu is equal to kinematic viscosity. So using this equation, we can find out what is delta. This is our objective. Then coming to seventh point, actually, the shear stress at any point, right? At any point on the flat plate, that is equal to tau naught is equal to CD star into half rho V square. This is the expression where CD star is equal to local drag coefficient. It is only at a particular point we are talking about. And this depends on Reynolds number. Reynolds number at that point, actually. Then if I want to give you an expression, CD star is equal to 0.664 divided by root rex. X is wherever you want to find out. So this is given by an eminent scientist, which mathematician Blasius. He has given this, actually, Blasius exact solution. Actually, this Blasius is the, what you call it as, he is the Prandtl's student. And Prandtl is father of modern fluid mechanics. Modern fluid. And Prandtl is the main person responsible for explaining this boundary layer theory. Next. So once knowing this, and you know what is Rex is equal to Vx by nu. X is always measured from leading edge. Right. Then the next point is, how many points we have finished? 7. So the eighth point. So we have discussed about the how to calculate the thickness of the laminar boundary layer, and how to calculate the shear stress at a point in the case of a laminar boundary layer. Now we will take how to calculate the drag force, on one side of the plate on one side of the plate that we are taking it up. So how to calculate on the one side of the plate? Now, basically, you know it already. Stress is obtained. Then naturally, force should be equal to that stress into basic area. That is how we go for it. So now already we know that basically the stress is equal to, already we have calculated, it is rho v square by 2. Basically, you are taking it into area. Area we have to take. Now, what is this CD? Because previously also we have talked about one CD, that is what we called at that time. That CD is the local drag coefficient, because when I calculate the shear stress, it is at a point I am calculating the shear stress. So at that point, how to calculate the shear stress? We have used the local drag coefficient. But if we come to basically the drag force on one side of the plate, that means on the entire plate, what is the drag force? The entire plate, it's not at one point, the whole plate. Then naturally, this CD is called as average drag coefficient. This is called as the average drag coefficient. That is only local drag coefficient. This is the average drag coefficient. So you now, problem is area is no problem, but only thing is how to calculate the average drag coefficient. How to calculate the average drag coefficient? The average drag coefficient CD is equal to, in the case of laminar boundary layer, it is 1.328 divided by REL. Again, compare it with the previous one where we have done for the shear stress. The local drag coefficient for is equal to 0.664 divided by root REX. That means we calculated the Reynolds number at X distance. That means at the point where we want to do it. At that distance only we have calculated the Reynolds number. But now when once you are calculating drag force, it is on the entire plate. Then you need to calculate the Reynolds number at the length L. That means at the edge of the plate. That means total length L you need to take it. So this is one you should remember actually in this case, where REL is equal to, yes, it is rho VL by mu, or it is equal to VL by nu. So this you should use. There, what is the thing? Rho Vx by mu. That x is limited distance from the leading edge, whereas here L is the total distance from the leading edge. So that is one difference actually while calculating the CD value. Remaining are all same, because this area is nothing but this area is equal to the length of the plate multiplied by the width of the plate. The length and width of the plate, if you take it, this is what we call it as area. So this is how we calculate the drag force. If suppose you want a drag force on both sides of the plate, drag force on both sides of the plate. So drag force on both sides of the plate, if you take it, how that will be also you should know it. For example, you take it, this is a plate, right? If you take this as a plate, now this is the free stream. Now this plate is kept in the free stream, which is moving at a velocity v. Now the boundary layer, laminar boundary layer is formed on the upper side. Again, the laminar boundary layer is formed on the lower side. So this is upper side, this is the lower side. So on both sides the things are. So naturally the drag force will be on both sides. Actually, the drag force will be there. On both sides of the plate, the drag force will be there. So in that case, the it is equal to total drag force is equal to 2 times FD. This is the only change that you should remember. That is equal to 2 into CD is the average drag coefficient, rho V square by 2 into area, that is fixed. So this is the thing actually. And remember, these equations are used, whatever the equations I have mentioned, take it from the beginning. In the case of a laminar boundary layer, the first thing is what is the thickness of laminar boundary layer. This is first thing, the thickness of laminar boundary layer. The thickness of laminar boundary layer is equal to basically what we mentioned, delta by x is equal to 4.91 divided by root Rex. Wherever you want to find the thickness at that place, Rex is nothing but it is the Reynolds number at that distance actually, or it is equal to Vx by no, or sometimes people will use it, or sometimes this also is okay, 5 by root r ex. So any one of these equations you can use it. This is the first point. The second point is the shear stress at any point. Shear stress at any point, right, in laminar boundary layer, right? So for that, shear stress is equal to tau naught is equal to CD star into rho v square by 2. This CD star is called as local drag coefficient because at that point x, local drag coefficient. And this local drag coefficient can be calculated as CD star is equal to, for example, 0.664 divided by root REX. Then the last thing is what is the drag force on one side of the plate, on one side of the plate. So drag side on one side of the plate is equal to FD is equal to CD into rho V square by 2 into area. This is what we should remember. Then what is CD is called as average drag coefficient. It is the average drag coefficient. So what is the average drag coefficient? That CD is equal to 1.328 divided by root REL, and REL is equal to rho VL by mu, or basically VL by nu. So this is one of the things. And fourth point is drag force on both sides of the plate. Drag force on both sides of the plate. Both sides of the plate. If you want to calculate drag force on both sides of the plate, then naturally total drag force is equal to 2 times FD. That is 2 into CD into rho V square by 2 into area. So this completes the laminar boundary layer. And all this is applicable as long as Reynolds number is less than 5 into 10 to the power of 5. In this basically portion, the boundary layer is a laminar boundary layer. Kindly remember that. So as long as the Reynolds number is less than 5 into 10 to the power of 5, you can use this actually for your thing. Okay. Now, the next case actually, we will take the next case actually, explain explain the characteristics of turbulent boundary layer and state equations to determine boundary layer thickness, shear stress at any point, and last, drag force on one side of the plate. This is the question. So now again let us go one after the other. What is first point? So the flow characteristics are turbulent flow characteristics. Within the turbulent boundary layer, the flow characteristics are turbulent flow characteristics. That is number one. Number two, the velocity distribution Previously, we wrote it is parabolic. Now, the velocity distribution is logarithmic. Very, very important. Now, third point is the thickness of the boundary layer varies. Delta is proportional to x to the power of 4 by 5, whereas previous one is delta is proportional to x to the power of half, where x is the distance from leading edge. This is another. Then the fourth point, the turbulent boundary layer exists from Reynolds number of 5 into 10 to the power of 5 to 10 to the power of 7. This is the thing basically. So turbulent boundary layer exists as long as the Reynolds number varies 5 into 10 to the, sorry, 10 to the 10 to the power of 7, but more than 5 into 10 to the power of 5, basically. This is basically Reynolds number, right? This is one. The next regular point. What is the thickness of turbulent boundary layer? It is again given by delta by x is equal to 0.376 divided by rex whole to the power of 1 by 5. There it is 1 by 2. Here it is 1 by 5. And rex, you know it, it is v into x by noon basically. And x is the distance from the leading edge, v is the velocity, nu is the kinematic viscosity. So this is the first. Next, what is the seventh? Shear stress at any point. Shear stress at any point tau naught is equal to, equation is same, CD star into half rho v square. CD star is called as local drag coefficient, and CD star is equal to 0.059 divided by rex whole to the power of 1 by 5. There all are 1 by 2. Here all are 1 by 5. That is the first difference you should find out. Then last eighth is then coming to the turbulent boundary layer. In case of the turbulent boundary layer, naturally the drag force on one side of the drag force on one side of the plate, on one side of the plate in case of turbulent boundary layer. Turbulent boundary layer. Again, here also, basically, FD is equal to, what should we write? Again, local drag, average drag coefficient into rho v square by 2 into area. This is the basic thing. And again, CD, we mentioned it as average drag coefficient. So, and average drag coefficient is 0.074 divided by REL to the power of 1 by 5. This is the next. So now what is the drag? Then basically, if you want drag force on both sides of the plate, drag force on both sides of the plate. If you take it, then naturally total drag force is equal to 2 times FT. That is 2 times CD into rho v square by 2 into area. So this is the second thing. So now basic the thing is, if the entire boundary layer is, for example, if suppose this is the plate, right? The entire boundary layer is only laminar boundary layer, for example. If the entire boundary layer is only laminar boundary layer, then we have found out the formula delta by x is equal to 4.91 divided by root rex that we have used for thickness. We have found tau naught is equal to cd star into rho v square by 2, and drag force is equal to, for example, then CD into rho v square by 2 into area. So is this CD star CD, this is basically this, from this if you take it, CD star is equal to local drag coefficient, which is equal to 0.664 divided by root rex. And if you take it, the average CD is equal to average drag coefficient, it is 1.328 divided by root REL. So this is all one angle, right? Whereas if you take it actually, both the complete boundary layer is turbulent boundary layer, right? If the complete boundary layer is a turbulent boundary layer, then we have again the same, we have done it, delta by x is equal to 0.376 divided by rex to the power of 1 by 5. The difference is it is for root, this is 1 by 1/5 of the power, that you should remember. Whereas the second one, shear stress tau naught is equal to cd star into rho v square by 2. And what this cd star is the local drag coefficient, and which is equal to 0.059 divided by rex to the power of 1 by 5, right? And third one is FD, drag force on one side of the plate is equal to CD into rho v square by 2 into area. So naturally this CD is called as average drag coefficient, and average drag coefficient is equal to 0.074 divided by REL. This is, you should remember, and this is what we calculated. And if we want both sides, you can do it. So this is if the entire boundary layer is laminar boundary layer, what should we do? If the entire boundary layer is turbulent boundary layer, what should we do? Both we discussed. And in all the both the cases, we are able to find out what is the thickness of the boundary layer, what is the shear stress and at a point, and what is the drag force on one side of the plate and drag force on both sides of the plate. My next question is, suppose if the boundary layer formed is like this. This is the stream, right? Initially it is laminar, then it became turbulent. So this is laminar boundary layer, this is turbulent boundary layer. Then in such a case, how you are going to take up the problem? So that means both LBL and turbulent boundary layer are there on the flat plate. Then in that case, how to find out? Kindly remember, in this case actually, so naturally, as far as number one, the thickness is concerned, use the respective formula. Use the respective formula. The meaning is you calculate basically the Reynolds number. As long as Reynolds number is 5 into less than 5 into 10 to the power of 5, you can treat that boundary layer as laminar boundary layer, and then you can calculate the thickness using that. If the Reynolds number is greater than 5 into 10 to the power of 5, at that place, for example, now the Reynolds number here, if you find out here, it is greater than 5 into 10 to the power of 5. Use the turbulent boundary layer and find out. So the thickness is only a local thing. Wherever you want to find the thickness, you first find the Reynolds number, depending on the define what is the boundary layer, and then depending on the boundary layer, you use that. So there is no problem. Similarly, as far as the shear stress is concerned, again use the respective formula. Again, why I am talking like this, the meaning is even in this shear stress, we are finding out the stress at a point. Actually, when you are finding out the stress at a point, so that point may lie within the laminar boundary layer or turbulent boundary layer, so you are very sure of it. So when you are sure of that point where it lies, automatically use the respective formula and calculate that. But now the real problem comes, what is the drag force on one side of the plate? The problem here is drag force is not calculated at one point. The force is calculated on the entire plate. On the entire plate, some portion is LBL, some portion is TBL. Shear stress is only at a point. Maybe here, maybe there. Thickness also, maybe here, maybe there. There's no, but drag force is on the entire plate. When you are using the drag force on the entire plate, so which average drag coefficient we have to use? Because drag force is equal to, you know it, FD is equal to CD into average drag coefficient into rho v square by 2 into area. So this is fixed. So now which drag coefficient, average drag coefficient we use, whether we have to use LBL, laminar boundary layer drag, average drag coefficient, or we are used turbulent boundary layer thing. So this is where the crux basically. So that is why actually in such a case, where both the laminar and turbulent boundary layers are forming, at that point actually we need to take the average drag coefficient like this. The average in such a case, average drag coefficient CD is equal to, you know, the turbulent boundary layer thing first, 0.074 divided by REL to the power of 1 by 5. So take that as it is first, minus 1700 divided by REL. So this is one of the important things that you should remember. Only thing is to account for the laminar boundary layer, this is there, and for the whole boundary layer is turbulent. This is the thing. So this is for turbulent boundary layer, you know it, and to account for that, we have kept it here. Using this, you can calculate the drag force. So remember, if both the boundary layers are formed on the plate, there any one of these things you can use it and complete your things. So with this, actually, the theory part of we defined what is laminar boundary layer. We defined about the turbulent boundary layer. So there, I really stop my lecture at this point. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.